Okay, so what we're going to do now is we're going to talk about activating and deactivating substituents on rings, and just some groundwork first. Okay, when we say activating substituents, it's anything that's on the ring that makes the reaction go faster than benzene. Okay, and if it's a deactivating substituent, it's anything on the ring, right, that makes it go slower, make the reaction rate go slower than on benzene. And there's generally the deactivating and activating substituents, there's two classes of substituents. There's electron donating substituents and there's electron withdrawing substituents. Okay? So methyl groups, right? Ooh, that's a nice color. I'll do this. Methyl group. Activating, electron donating or electron withdrawing. Donating through hyperconjugation because it's got the sigma bonds, and as they rotate around, they line up with the p orbitals on that carbon that's next to it, and that electron density is pushed in. Okay, so this is a donating group. I'm going to have to write with my finger because this thing doesn't. Oh, I know. Maybe I'll put a little chalk on it, and it won't be so sticky. Ooh, that's better. Donating groups. So it's activating. Hang on.
Can I say that?
Go ahead, go ahead.
Yeah, can you explain why it's donating?
Yeah. Just a kind of a review. Okay, so these are the carbons on a benzene ring, okay? And these are the p orbitals on the benzene ring. And where I just made that mark with my finger, that's where the pi bonds conjugate and makes the aromatic ring, okay? Over here, I have a methyl group. But it's anything that has sigma bonds on it, okay? And so those are connected by sp3 hybridized. Okay. So the little circles, I'll do them in blue, how's that? Those little circles represent hydrogens. And so this carbon, that's this carbon, okay, is bonded to this carbon here. That's, if I can get this thing to work, that carbon. All right, now, as this group rotates around, all right, so this is going around and around and around, and I can't do that, of course. Every once in a while, it lines up with this p orbital, and when it lines up with that p orbital, the electron density in the bond transfers or is connected to the electron density of the ring. And when it does that, that induces electron density into the ring. So it's an electron donating group. We say by hyperconjugation. Some people will call it an inductive effect. Okay, but it's just through space. So it's kind of like, you know, here's an analogy. Like if I took a balloon and I rubbed it on my head, what would happen to the balloon besides get dirty? What would happen to the balloon? Static, right? But if the balloon has static electricity on it, and I start bringing it close to you, ignoring the fact that it's rubbed my head, right? At some point it would get close enough to you, you could feel like the static. You could feel the electrons either pushing or pulling on the hairs in your body, right? Because that's the furthest thing out from your body. That's what hyperconjugation is like. It's an electric field effect. It's pushing electron densities into the ring. And so it turns out that effect, even though it sounds like, oh, how much could that be, right? Makes, like toluene, this is toluene, when it undergoes nitration, is 25 times faster than benzene. So just having that one group on it donates enough electron density to the ring that the reaction was 25 times faster. Okay? Yeah. So when you learn about it, like in the first semester, you're usually like, whatever. I have to memorize it. This is what it does. But it's an important effect. It has a lot of impact during the course of the semester. Okay, so, sorry, I just came up with the static balloon thing. It probably was new to everyone. I don't know, was that a good analogy for it? Yeah, okay, good. All right. So that's why it's important you ask questions, because it gives me a chance to, like, try out new ideas. And I got to incorporate a balloon, and you know my balloons are my favorite prop in my classes, so. Okay.
Next time you need to bring one out.
Yeah.
I'll just show you.
Well, if I'd have known he was going to ask the question and that was my response, I would have done that. Huh? Yeah, that's too much work now. Okay. So, electron donating effects. Now, here's the thing. Put an electron donating group, toluene, nitration, onto benzene, it is 25 times faster, but not in all positions on the ring. You'll notice that when you do the nitration of toluene, 63% of the product, right, is in the ortho position, 3% is in the meta position, and 34% is in the para position. So even though it's 25 times faster, it's 25 times faster combined in essence in the ortho and para positions, and it's much slower in the meta position. So this is why, generally speaking, activating substituents are called ortho-para directors, because instead of having meta in the product, you have ortho and para. Okay? Yes, that's a great question. That's the follow-up question.
Why?
I was waiting for somebody to say, why? That's why I just stood there and looked like a... Yeah. Anyways, I don't know what I was going to say I looked like, but I looked like a chemistry teacher waiting for a question. Okay.
You want to know why?
Okay. It's not like my why we use Y as the electrophile, why not, right? That was a stupid joke. This is actually real. Okay, so watch what happens. This is the mechanism, and these take a long time to draw, so I'm going to walk you through them rather than draw them all. Let's say we're going to go through, to understand why it does that, we're going to go through each mechanism as if it attaches to ortho, meta, and para, and we're going to compare the intermediates to try to understand why ortho and para are favored. Okay? So hang on to your question for just a second. Yeah. You did. And you did the simulations, and you should have answered the question then.
All right, just making sure.
Yes.
What was the name that you called it again?
Ortho-para directors. I told you I was going to cover this later, but I said you should read ahead. And when you did the simulations and you calculated the energies for anisole, you found out ortho and para were a lot lower in energy. All right, so here we go. See, I plan my labs that way. Okay, so look what happens. Attaches to the ortho position. 3 resonance structures, right? This is the special one. They highlight it for you. I wouldn't have. I would have asked you to figure out which one's the special one. That's the special one for you. Why is that one special? Tertiary carbocation. You got an electron donating effect next to a carbocation. This one is stable. Okay? So, does that mean that's the reason why it's more reactive than meta? We don't know yet. Because you have to draw meta and ask the same question. Okay? So just knowing that, oh, that's more stable, that's why it is, you also have to show that when it adds to the meta position or the para positions, that meta is different and para is the same. So here's the other two. Here's the meta attack. So when it attacks in the meta position, right, you get a positive charge here. Then resonance takes the positive charge next to here and to here. So you never end up with that tertiary carbocation on the ring. You never get that electron or inductive effect to stabilize the positive charge. So in comparison to ortho, ortho is going to be more stable, right, than meta, because it has hyperconjugation. It has the tertiary carbocation, right? So this one is stable because the positive charge by resonance shows up at the tertiary position. This one's less stable because you never get that. And then if you do para, I feel like I'm yelling. Try to be relaxed. But if you do para, what happens? Well, it attacks the para position, first resonance structure. Either way, right? If you attack para here, either way, you get a positive charge at the tertiary position. So this structure is more stable. So you expect, right, ortho and para to be lower in energy than meta because of the tertiary carbocation. Okay. So that explains why you have more ortho and para than meta. Why, now that's the next question, right? Why more ortho than para? Now let's analyze what's going on here, okay? Hang on. No, it does. No, that's not it. Look at this, okay? They're next to each other, right? I'm being a little misleading. And you do this one, and they're far apart from each other. Think about sterics. What would that argue? You don't want them next to each other. You want them farther apart. But what happens? They're close to each other. So that's not it. It's not sterics. Okay, so you guys remember kinetic molecular, or Arrhenius theory? Chem 1b? Do you remember, what are the things in, sorry, not kinetic molecular theory, but it's part of collision theory. It's a good topic, because I just got collided in my car.
Oh, I know why. It's because there are two main positions, but only one position.
Two ortho positions, yeah, because in collision theory, K is A e to the minus E A over RT. Okay? Look at this. If you look at the potential energy diagrams for the ortho position is higher in energy. It's because of sterics. The two groups are attaching next to each other, right? But there's two of them, right? And in this part, this is the activation energy that we're seeing in this graph over here. This is EA. But in the other part of this equation, you have A, that's the orientation factor, like the percentage of times they run into each other and they're like correctly oriented. And it's the frequency of collisions. And so you can collide with the ortho position twice as much as the para position. Okay, so having said that, that explains why ortho is a higher percentage than para. But here's the thing. If you make it just a little bit bigger, okay, I don't think they have the numbers on here. This will be predominantly para. Yeah, the substituent, the electron donating group on the ring, if you make it slightly bigger, okay, even though it's ortho-para directing, the sterics becomes a big enough factor that it pushes it into the para position. Which is why having something like, since we brought it up, using sulfonates as blocking agents for the para position is an important aspect of synthesis, because you can then direct things to the ortho position even if the activating substituent is large. It's not necessarily efficient, it's not necessarily fast, but it keeps, but it'll make it happen. Yeah. Okay, so it turns out induction through resonance is a bigger effect than induction like hyperconjugation. And it's pretty easy to see why. Okay, don't ignore the slide for now. I'll come back to it. But I just wanted to get induction is a more important aspect. Hang on. I'm having desktop connection issues. There we go. Here we go. So, nitration of anisole. Okay. Remember, what's that? Is this making sense now with the lab or something?
It is, but we're also making.
The computer was making a noise? Oh, you know what? I made California rolls last night. They were delicious. I did.
Is that what?
Just a few.
Chinese food?
No, that's just I'm sweating. So, I eat so much Japanese food, you know, it's just one of those things that. Sorry. Okay. So ortho attack, right? You notice what happens in the ortho attack when you have an electron donating group that has a lone pair. So the important aspect of this is these kinds of electron donating groups is this anisole has a lone pair there. That's a gigantic lone pair. Okay. And because of this lone pair here, once you form this carbocation, right, this lone pair can participate in resonance and delocalize the charge over one more atom or one more bond. And the more resonance structures that you have, the more stable it becomes. Okay? So if you look at the ortho addition or the para position, each one of those allows a positive charge to show up next to the electron donating group. And because it's next to it, right, produces an additional resonance structure which gives it more stability. Again, when you do it, ortho-pair director, and you put something in the meta position, that positive charge never shows up next to that lone pair. So you don't get the additional resonance structure, and so the reaction rate is slower. So if you look at it, this is what the ortho, energy diagram looks like. The potential energy, this is the activation energy to the intermediate. This is meta, is much higher, okay? And this is para, and para is much lower. And the para product becomes a major product because of lower activation energy because of sterics. Even though there's still two ortho positions to add to. Go ahead, Eric.
Can you go back to the last slide?
Mm-hmm. Yes.
Why would you even put a positive charge on oxygen? This is both of it.
It's right. So oxygen positive charge is not the best thing, but it still can delocalize. It's a very common, right? It's a very common delocalization pattern. It's an allylic pattern, essentially. Yeah. And it doesn't have that when you do it meta. So as a result, even though, right, it's on the positive charge is on the oxygen, and it's not the best thing, one of the things that structure does do that's really good is it satisfies the octet rule for everything. Right? Because normally when you have a carbocation, right, 6 electrons. Positive charge on an oxygen versus non-octet, you'd rather have charge on the oxygen and satisfy the octet rule. And I think we talked about that kind of a little bit last semester too. Okay, so go back. Here's one other aspect of this reaction that I think is really cool. If you just draw the resonance structures for anisole, this is without the attack of the electrophile. Where do you notice the negative charge showing up on the ring? Ortho and para. So if you were to draw the resonance hybrid for one of these things, sorry. You would draw dashed lines like that and a dashed line here. You have partial negatives there partial negative there, and a partial negative here. Come on, draw. There you go. Where do you think the electrophile prefers to be attached to before the reaction starts? Right? It prefers to be attached to where the high electron density is. So it directs, even like before the reaction takes place and we look at the intermediates, there's charge on the ring that helps direct the electrophile to those positions. Okay. Anisole is so strongly, remember I said methyl groups or alkyl groups are not as strongly activating as lone pair, something with lone pairs on it. Right. Anisole is so strongly activated, if you wanted to do bromination, you usually can't get one bromine to show up. It usually brominates multiple times without a catalyst. Right? So you don't even need the catalyst to make the reaction take place. Just because the electron density in the ring is so high, it's strong. It's a strong enough nucleophile to attack BR2.
Could using NBS avoid the polyhalogen?
No, I don't.
Would it just take
I don't know. Yeah, well, you'd be using NBS to generate really low concentrations of BR2. So the answer is, I don't know. Might. I will try to find an answer. Put it on a piece of paper at the end of the class and stuff it in the box. Okay. Really quickly before I do this, I want to do something. I'll do it on my iPad so that you guys have it. Wow, you know that new projector makes like all the difference in the world. I don't feel like I can't see stuff when I'm writing it, or you can't see stuff when I'm writing it. That's kind of thing is always in the back of my head. Whether or not you understand it, I mean, that's a whole different. As long as you can see it, I'm happy. If you understand it, that's whatever. I think I need more coffee. So, electron donating groups, all right, are not all the same. We already saw that. So what I wanted to do really quickly is I want to draw, like, let's see, which way should I put? I'm going to make okay, let me do this. I'll let you guys decide which way I draw this. And if you don't like it, well, too bad. You decided. So this is a reaction rate. Oh, this pen's not working really well. My finger works even less well. Reaction rate. Hang on. Now I know why this one was in the drawer at home. Okay. Put a line here. This is benzene. And what I'm going to do is I'm going to throw other substituents up there, and we're going to decide whether or not they're faster than benzene or slower than benzene, or faster than each other or slower than each other. So we've already talked about alkyl, right? Do you want the alkyl to, you want faster to be to the right or to the left of benzene? To the right, okay. I didn't leave much room over there, but that's okay. So this is substituents on the top, right now at least, R groups. Those are the least activating substituents that we have, okay? So they're the closest to benzene. We already decided that oxygen is a better activator, right? Because it has the lone pair. So that should be further to the right. So I'm going to put it right here. And I'm going to put one lone pair on it to remind ourselves. It looks like somebody's screaming again. Remind ourselves that they're more strongly activating because the lone pair can donate to the ring. Okay? So now, this is what you have to decide. Nitrogen. More activating or less activating? And you need to just not just say it, but you need to argue why. So, yes, say it again.
It has a lone pair, but it's less electronegative.
Has a lone pair, but it's less electronegative. Right. So intuitively, it kind of sounds like it should be left or right of oxygen? To the right. Okay, so intuitively, we kind of understand the lone pair donates, but the nitrogen, through the bond in its electronegativity, pulls electron density out. So there's two competing factors. All right? How strongly it pulls electron density out through electronegativity, and how well it donates electron density back through its lone pair. If I was going to put fluorine on there, where do you think fluorine would go? Potentially, well, in terms of like in generalities, to the left, right? Right. So here's the thing. Remember, fluorine's got the highest electronegativity on the periodic table, and still it has the lone pair that it can donate. Turns out it's a deactivating group. So if you put fluorine on this list, it's deactivating. It's deactivating because what happens is its ability to draw electron density away from the ring is greater than its ability to donate it back. Okay. Okay, so on the bottom, I'm going to draw some more complicated groups. Let's say the benzene ring is connected like this. So this is the ester functional group. So it's going to be near oxygen, probably. But now is it to the left of oxygen or is it to the right of oxygen?
It looks like because it's resonates, it's gonna pull electrons to the right, away.
Say that again?
Because the double bond on the oxygen will pull the electrons away from the benzene.
So it has resonance structures, right? The electrons could go to the right or they could go to the left. I don't know if you about you, but I just constantly see faces in everything that I draw. So more activating or less activating? Less, because the lone pair can spend less time over here. Okay. Nitrogen can be involved in what are known as amide bonds. So I could have a nitrogen, but it can be connected to, let's say, a hydrogen, because you still have to have something else up here. It could be other things. Something like that. And then here it's connected to the benzene ring. Okay? Similar argument, right? That lone pair can't participate in resonance as well to the ring, so it's got to be somewhere in here. I used to use the analogy, I'll just tell you the analogy because it's kind of funny. Like when you're young and you're like junior high age, and you say you hang out with the girl, and you're like having a great time, and you like enjoy talking to each other, and all of a sudden, oh, there's this other girl. And you're hanging out with this other girl, and you don't realize that you were actually like a boyfriend, girlfriend with the other girl because you're stupid. Right? You know, like teenage boys? This is a teenage boy. See the face? So he's trying to donate his electron pair, sorry, straight face, to the benzene ring and the carbonyl group at the same time, and he's just not as effective. I don't know why you guys are all laughing so hard.
You said straight face.
Is it true? The reality
I would have noticed nothing unless you said straight face.
Right? Sorry.
Can you say why nitrogen is so far to the right?
Oh, remember, this is more activating, less electronegative than oxygen, but still has a lone pair. You could also think of it as nitrogen's better at holding a positive charge, the thing you talked about before. Better at holding a positive charge in the resonance structures because it's less electronegative. If you look at this trend, excluding the R groups over here, this is just the periodic table. Nitrogen, oxygen, fluorine. It's electronegativity on the periodic table.
So would like a sulfide group would be like towards the far right?
Yeah, so I'm not even sure how far right. Oh, sulfide? Like S minus?
No, like S.
SH.
Yeah.
Okay. I'm not even sure exactly where it would fit. It's going to probably be an activating substituent, but it's going to be pretty close to benzene, I think. I'll have to look it up. The reason being, sulfur is so big that it can't donate electron density back to the ring efficiently. We'll see this with the halogens. I'll have to look that one up, so if you write that down, I'll look it up.
Is that the same argument with the pi bonds are different sizes?
Yeah, the p orbitals are different sizes. If the p orbitals are the same size, the electron donation back is more efficient. So fluorine's actually more efficient at donating electron density back than bromine or iodine or chlorine. Okay. So we'll get to those guys later. We'll see how far we get today. So all activating, except for fluorine up there. But here's the thing. I'm going to make this generic. I'm going to make this X. Okay? So that's all the halogens. I'm just going to lump them all together. Because they have a lone pair, they're all ortho-para-directors. Because when the carbocation shows up next to the substituent, there's another resonance structure there. That make sense? Should I draw it? I'll draw it real quick. Here's a benzene ring. This is the electrophile that's attached. It has a lone pair. Sorry, not the electrophile. This is my substituent, so I'm just going to call it X with a lone pair. My electrophile is added here, so I have a positive charge here, and then the other parts of the ring look like that. So that's after the electrophilic attack. This lone pair provides an additional resonance structure, which makes the ortho and para positions more stable. Okay, so in general, all the activating substituents are ortho-para directing. Okay, that's in general, and the exception for ortho-para directing is that fluorine, even though it's a deactivator, is ortho-para directing, or chlorine or bromine. So all the halogens are ortho-para directing. So what I've done on the screen up here, right? Everything from here to here, out that way, this is all ortho-para. So all activating substituents are ortho-para directing, and there's one deactivating substituent that's ortho-para directing, at least the ones that we deal with. Questions on that? So we're going to cover a little bit of synthesis strategy. Oh, that's weird. There we go. A little bit of synthesis strategy. We're going to start, you're going to get a lot of problems that say, here's benzene, make this, okay? Now, in the very early part of the chapter, here's benzene, make this, it has one substituent, all you have to do is come up with reagents, right? Oh, it's a nitration, or a sulfonation, or acylation, or alkylation, or bromination, or blah, blah, blah. Okay, but if you want to make this, you have to plan your synthesis. So you notice the substituent that's on here, right? This group, ortho-para-directing. This group, we haven't really talked about it yet, but there's things called meta-directors. This will direct to the meta position. And it turns out all the deactivating substituents, except the halogens, are meta-directors. Okay? And we haven't gone over the properties of deactivators, deactivating substituents. But this is one of them. Which group was put on last? The NO2. The nitro group was put on last because they have orthopara orientation. All right, so it's para in this case. But because it looks para, that means the para-directing group, orthopara-directing group, the para-directing group was there first. So you look at the orientation, and you say, oh, it's para. Right? You look at your substituents, and you see whether or not it makes a difference. If you have a meta-director like it is here and an orthopara-director there, orthopara was added and then meta was added. Yeah, it would be in the meta position, but you can't actually do that because it's too deactivated. It won't actually act. Yeah. So now what you have to do is you have to come up with a sequence of reactions. This is a little bit misleading because they only show 2 arrows. It's actually 3 arrows. How would you make that then? Right? So you know, practically speaking, add this first. Color, I'll use, ooh, I bet this will show up now. It's purple. You're going to add that one first. You're going to add that one second. Okay? So if this is the first thing you're adding, then you're adding it to the benzene ring. What do you use to add that? And it's actually 2 steps to add that. No, you don't have to brominate it. No.
Start off.
Discuss amongst yourself for a second and then say something.
Is it like the acetyl chloride with the R group on it, and then you use zinc to reduce it?
Yeah. Okay, so you can't do the alkylation reaction because you're going to end, if you do the alkylation reaction, whatever, X is the halogen, right? It'll rearrange. The carbocation that you'll get is that one. So you have to do acylation first, okay? So if you're going to do acylation first, then you'll have to do the reduction after. So the first step, and this is a horrible writing. I don't know why people just don't throw these things away. You're going to add catalyst, like aluminum chloride, all right? And then the reagent will be yeah. Nope, yep. That's it. And then second step for that step is that Clemenson reduction. It's the mercury amalgam. It's HCl and zinc and mercury. And a brief disclaimer, I thought I knew the mechanism for this reaction. I thought it went through like a partial reduction to an alcohol. And so then I went and looked at it, and it's not that. And the reason they know that it's not through the partial reduction to form an alcohol is you do the same reaction with an alcohol, nothing happens.
Is there a way you could stick the methyl group on and then do like a grain yard or something to attach the T-butyl group on it?
Yes. You could do a methylation, and then you could do a bromination, and then you can make a Grignard, and then you could react it with acetone, and then you could oxidize it, and then you could do a Clemmensen reduction, and then you would be to the same place that you are now after 2 steps. But yes, the answer is yes, you can do all that. Should you? No. Right? You have a hard enough time getting a good yield with only like 1 step. Can you imagine what it's like doing like 10 steps?
Or about a kilogram instead of a milligram?
Yeah. Start with a kilo, end with a milligram. I have to say, this is my 1 second of bragging. My son, James, can start with a kilogram of stuff and end with like 90+% yield on all kinds of reactions. Yeah, but you know what part of the trick is? When you start with like a kilogram of material, because he's making those insect pheromone things, when you start with a kilogram of material and you lose a gram, who cares? But if you start with, like you guys, 200 milligrams of product and then there's stuff's left on the walls of your container, you've just lost 10% of your yield. And there's all kinds of fun things he gets to do. You know how you guys do extractions, right? They actually make extraction pads, these big like pieces of like cloth almost with the absorbent on there. And all he does is he takes his reaction vessel and he pours it onto this pad and it soaks up all the junk. He washes it with solvent and then he extracts the pad. Isn't that cool? Yeah, I'm like, and all that work you guys do? Psh, that's okay. You're learning principles of how to do it. So, what's the second step after this? Is just the nitration step, right? So, sorry. That was my bragging on my son bit. So, HNO3, H2SO4. Yeah, when he tells me like the scales of things that I'm just doing, I just shake my head like, yeah, we don't do that. Okay. All right, deactivate. Dang it. There we go. Deactivating groups. Okay, nitro is a deactivating substituent. And it's a meta-director. It's deactivating because, right, if you look, oh, sorry, it doesn't show it on here. Let me draw it up here. So briefly summarize for me why activating substituents in one sentence are activating. Activating substituents donate electrons. So what does that mean about deactivating? They pull out electron, right? They remove electrons. So nitro, in fact, is one of the best or strongest deactivating substituents. It has a lot of features on it that you'll see in other deactivating substituents. So when you draw nitro, you draw it like this. What is deactivating about that? It's got a resonance structure and this positive charge. So nitros are very strongly deactivating. Because positive charge next to the ring and also by resonance removes electron density. That is, you can do this. You would. But it can still do that. No, it's not happening. But it can still do that. Unlike the other substituents that don't do anything like that, right? So just the act of being able to pull electron density out deactivates the ring. Also, there's intermediates that are destabilized. I'll show you the intermediates that will help you understand. Okay, so charge next to the ring, and it can also remove electron density by resonance. Okay. So to help you recognize, now that I've put those things up there, these are features that you see in deactivating substituents. So if you have a double bond next to the ring, or a triple bond next to the ring, with a more electronegative group. Sorry, get fault right there. Oh, there's nothing there. Those both can, by resonance, remove electron density from the ring. Both are deactivating substituents. And nitrogen, right? 4 groups on the nitrogen, positive charge. That's also a very strongly deactivating substituent. So one of the interesting things about amines is deactivating when it's protonated, activating when it's not protonated. Just by changing the pH, you can change whether or not it's an ortho-para director or a meta director. Presuming that you can do the reactions that you want under those conditions. Okay. So let's look at deactivating substituent, the nitro group, right? Look at the ortho attack, the very top up here. Positive charge, right? Where does it show up? Right next to another positive charge, right? Very unstable. Again, ortho-para addition always puts a positive charge at the substituent. Right? It's the same as this is a meta-director. It's the same as a meta-director. It's just that because this is an electron withdrawing group, it destabilizes this resonance structure. If you do it in the meta position here, right? Positive charge is here, it's here, and it's here. So it never actually gets right next to the electron withdrawing group, and as a result, is not destabilized by those two positive charges being next to each other. The para attack, right? It just takes one resonance structure. The positive charge now is at the nitro group. And as a result, this resonance structure is destabilized. Okay? So the reactions go slower, but they go really slow in the ortho and the para position because of the positive charges being next to each other. Right? So this is like you're running a race. Right? But instead of you going faster to win, everybody else goes slower. Or no, everybody feels sorry for you because you're so slow. That's the only way I would have won a race. My kids are all really fast. They got that from my wife. Wait, I'm just thinking about it. Never mind. Okay, so the ortho attack and the para attack, right? Destabilized, slower. Meta attack isn't really fast. It's actually slower than if you have an activating or no substituent on it, but it's just not as slow. And the analogy of you're in a race and everybody slows down so you can win, that's what that is. Okay. Halogens are the exception, of course. We already talked about that. I introduced that idea. Halogens are the exception because you can generate another resonance structure with the halogens. That's enough, right, stabilization in that ortho and para position to make ortho and para faster than meta, even though it's slower overall than benzene. So what I'd like to do, I wonder if how far back in my drawings I can go. Oh, can't go that far back, okay. Another diagram. Whoa, that's purple. Hang on. Oh, this thing's horrible. Okay, number line. And I already did benzene. So I'm going to put benzene to the far right so I have more room to space things out. Because I already told you like how to predict activating and deactivating substituents, or activating substituents, and whether or not they're better activators or worse activators. Okay. So now we're going to do deactivating substituents. So I'm going to put a benzene ring over here. Halogens are over here. Put it at the top. Okay. We see carbonyl groups a lot as deactivators. So let's say you have this, and we want to know, and remember we said I don't know if I said it. Hang on. Let me draw another one. We want to place this. So that would be an example of a deactivated ring. That carbonyl acetophenone, that's called acetophenone. I think we used it the other day in class. But acetophenone is deactivated. Why is it deactivating? It removes electron density by resonance, right? It also has the oxygen, which is electronegative, so that gives it a little bit of an inductive effect. What happens if I put another oxygen over here? Let's say it's a carboxylic acid. Should that be to the left, that is less active, or should it be to the right, should it be more active? I mean, it's kind of a coin flip, right? We did. But it was next to the benzene ring as an activating substituent. Right? So the carbonyl is drawing out electron density, right? So this is drawing out electron density here. But this is donating electron density back. Now, you could argue this two ways. You could say it's to the left or to the right. Like you guys said left immediately because oxygen's very electronegative, right? But as it turns out, it donates electron density just as well as it takes electron density back. And as a result, this double bond can't pull electrons as efficiently from the ring because it's also resonating with this one. Okay? That was supposed to be an arrow and it stopped drawing. So it actually goes over here somewhere.
Before or after hydrogen, deprotonated, does that make a difference?
Yeah, deprotonating probably makes it less deactivating because there's more electron density on the oxygen to donate back. Yeah. I should have put an R group there. That's a lot easier to talk about. Nitro, we said, is really strongly deactivating, right? So NO2, that's both an inductive effect and a a resonance effect, right? So NO2, because of the positive charge, plus resonance. Turns out NH4 plus, like R, oh gosh, it's so hard to draw with this pen. NH3 plus, or NR3 plus, okay? That's very strongly deactivating too. It's not as strong as a nitro, but it's somewhere in between a carbonyl and a nitro group. One of the most strongly deactivating substituents, these ones are a little harder to predict, except for the ones that have the oxygen lone pairs, like the lone pairs next to the carbonyl. Those are pretty simple. Other really strong deactivating substituents turn out to be things like this. It's purely an inductive effect. Okay? So the inductive effect of charge is pretty strong at deactivating the ring. Other strongly deactivating substituents way over on the really deactivating side are things like this. So you have an inductive effect from the fluorine, and you also have an electron withdrawing effect from the carbonyl group. Okay. So those all fall in, those are really inact or deactivated rings. Weird. My computer's doing funny things. That's actually as far as I wanted to get, but let's go ahead and let's do this real quick. We're just going to do it on the board because this thing is so hard to write with. And I'll probably start with this as well, and I'll have something better to write with. Oh, actually, you know what? I just realized. I'll pass out the pieces of paper that'll burn out my 1 minute time. Sorry I didn't get around to answering these last time. I will have stuff for you next time we get together. We'll finish this material on Monday.
Are we going to get an extra day of lab? Because this is technically our third day.
Yeah, you do 4 days. I'm actually thinking about adding another day. We'll see how today goes.
So we'll go till Wednesday.
Huh?
So we'll go till Wednesday.
Is this our third day?
Yeah.
You're supposed to get 4 days.
Yes.
For this lab. Pass the papers. I know. You can do all of them again, and then you can collect them all when you're done.